Hello everyone, this is Srihashwardhan. I'm a fourth year computer science and engineering student at SM University AP, specialized in big data analytics. Today, as part of information retrieval course, let's try to understand cover trees. So here comes agenda of our presentation. We'll start with prerequisites that are required to understand cover trees very much. And then we'll move towards the origin of cover tree. Later on, we'll discuss about NN problem. Then we'll move to cover trees, core concept of cover trees. We'll move to the time complexity analysis. Later on, towards the end of our presentation, we'll try to see a problem where we build a cover tree using points of coordinate axis. So here comes our first prerequisite. It is about a ball. Ball is simply a set of all points that fall within the circumference of circle. For suppose, let's have a circle with radius r, center point A, and then what we can say is all the points that fall within the circumference of circle belongs to that particular ball. So this is about the ball. Next, try to understand what are the next prerequisites. So here comes the next prerequisites. They are about cover, packing, and nexting. We'll go towards each point and let's try to understand it properly. So cover is nothing but a collection of balls that make sure that each and every point in the particular coordinate plane is covered by at least one ball. So what we'll try to do is it will make sure that no point is left behind and every point is minimum covered by at least one ball. And next thing is about packing. Packing is quite different from covers. We can sell it as quite opposite from cover. So what it will do is uh, it will make sure that no two points are so close to each other. So let's try to see what is the definition here, and then let's try to understand by examples. So what it is saying here is a packing is a set of points, especially in our case, it is about centers of region or cluster that are well separated. That is, no two points are not too close. So what's the situation behind this? So let's think we have very close points in a coordinate plane. So finding the nearest distance or making clusters could become so easy. So then comes the concept of packing. It makes sure that no two points are too close, so that finding the distance between 2 points or making clusters could be so easy. Next thing is regarding nesting. Nesting ensures that all the points in a higher level are part of lower level also. So let's see what is happening here. As you can see here, these four are four different levels. What is saying is L3 is subset of L2, or L1 is a subset of L2, and also L0 is subset of L1. What you're trying to say here is all the point in higher level will also be the point of lower level. So we'll make sure that no point is lost in the higher level. It will move to the next levels also. So next part is regarding hierarchical partitioning. It is one of the important concept in our situation because let's try to understand why. So for suppose let us have a coordinate plane consists of many hundreds and millions of points. So finding the nearest point for a particular point could be so difficult because we need to go towards each and every point and calculate the distance. Calculating distance may have different formulas like Euclidean, Hamilton, Hamilton. It have many, sorry, Euclidean distance on Manhattan distance. So even though we have different kinds of formulas, but going towards each and every point and find the distance could be so hectic task in the case of hundreds and millions of points. Each comparison would take order of n time, and when n is so large, it is computationally so expensive. So we'll follow the technique called hierarchical partitioning. So let's try to understand with a small example in the next slide. So as you can see here, what is happening here is we have 5 points. Let's name them as A, B, C, D. We're not considering about their particular position. Let's try to understand with these alphabets. So for suppose let's think in the coordinate plane, we have A, B, C, D, E, where A, B, C were close to each other, and then D, E were close to each other. So what will happen is we'll try to divide them into two particular clusters. One cluster has ABC, other cluster has DC. Now what will happen is let's consider this one as partition level 1. So let's now move towards partition level 2. What will happen at partition level 2 is we'll try to break down the clusters that were created in partition level 1 in the partition level 2 into under further more detail. So what will happen here is among ABC, we'll try to find 2 points that are too close to each other. So in our example, let us think that AB are close to each other and C is also close to A and C, but AB are more close to each other. So we'll make AB as one cluster and C as one cluster. And then we'll move towards the right side cluster in partition level 1. What will happen here is since there are only 2 points left, so we'll leave the cluster as it is. So Now after two partitionings, like two partition levels, this is the structure that we got. What happened here is we have totally two clusters. One is left cluster and right cluster, where left cluster has ABC, right cluster has DE, and ABC is further divided into A, B, and C. Now what will happen is whenever we get a point, for suppose we get a point as RS. Now what will happen is first we'll try to understand which cluster is very close to RS, or whether it may be ABC, whether it may be DE. So what will happen is whenever we get one particular cluster that is close to RS, we will just look towards only that cluster, so that it eliminates other cluster, and then the total computations that we require gradually decreases. So this is what I try to explain by writing the points down here. So I hope hierarchical clustering is understood by everyone. Now let's move to the next point. So finally, we complete the prerequisites, and then we are into the next part, that is about what is the or we trying to understand what are the origins of cover tree. Cover tree was first introduced by Elena Sham-Kagaday and John Langford in their research work published at ICML 2006. It is a very popular conference. It is International Conference on Machine Learning. It actually held in Pennsylvania of US. So the first initial contributions of cover tree was published as a research paper titled as Cover Tree for Nearest Neighbor Search. So let's move forward and understand what is nearest neighbor search and then what is the problem behind it. So here comes the end problem. Definition is given that given a dataset S of endpoints and distance function B of X and Y, we need to find a point Q that belongs to dataset S that is closest to query point P. So what is trying to tell is, for suppose we have 100 points and then we got new point to, and we need to find the distance to nearest neighbor to the new point among 100 points. So now what we'll be trying to do here is we'll be going towards the each point and we'll be trying to find the distance between new point and the already existing point. So this is what finding the nearest neighbor would actually work. This is very famous as being taught in the most of the machine learning models like KNN. So let's try to see what is the problem. As I already told in the hierarchical clustering, the main problem here is going and finding the distance for each problem. So this is what I try to mention in the challenges. Brute force search compare P with each and every point. So it will take order of n complexity for one query, and then it can be computationally highly expensive for large and high dimensional data sets. This is one of the problems. This is one of the main problem happening here. So to overcome this, we need to have few data structures like cover trees and k trees that are needed to speed up the search. So the one point that we need to discuss here is the efficient data structures that we are talking here about cover trees and k trees. All of them follow hierarchical partitioning. But the thing is how they are trying to partition the points and how they are trying to create the levels would make the difference. So we'll try to understand why cover trees is better than k trees and all such kind of things in future slides. For now, this is about NN problem. Let's try to move forward and try to understand what are cover trees and what are the points in the cover trees. So here comes the core concept of cover tree. So cover tree is an hierarchical data structure built over data set, and it is so efficient to find the nearest neighbor search. So what will happen here in the cover trees is, in cover tree, we'll try to divide the data points in different levels. And then all these data points will belong to a particular data set, and they are arranged in different levels. As you can see here, there are different levels of point arranged here. And then what will happen is at the higher level, we'll get only cursor view of the data, but in the lower level, like in the lowest level, we'll get the more detailed view of data. And then for each and every cover tree that is built, it need to follow three particular properties we could set as properties. They were nesting property, covering property, and then separation property. Most of them we previously understood in the prerequisites. Now let's try to understand deep in the context of cover trees. So here comes the main concepts of the cover tree. There were three, starting with the nesting property. What will happen is for each level, the above level, the below level must be the subset of the above level. What I'm trying to mention here is, for suppose let's have value C1 in this level, C2 in this level. So the value C2 must be carrying to the next level also. So this is what nesting property means. It ensures that, for suppose if a point comes at a particular level, it will be going through each and every level. It remains at all the lower levels. So it makes lower level more finer, and it is providing more information in the lower levels. Next thing is about covering property. Every point in every point is covered by parent in ci level within distance of less than 2 power I. So what do I actually mean is, so a parent and the child must have a distance less than 2 power I in the coordinate plane. This is what covering property mentions. So it ensures that lower level points lie within bounded distance from their parents. So it will be useful for searching nearest neighbor. And then we have third property is it is regarding separation property. So what is trying to mention here is distant points at same level are separated, like or well separated. That is, the two different points within the same level must have distance greater than 2 power I. Here I is a index of the level. So let's try to once again see the difference between covering property and separation property. So covering property is telling that the distance between parent and child must be less than or equal to maybe 2 power I. And then in case of separation property, the distance between we can call it a sibling, the distance between siblings should be greater than 2 power I. This is what the core properties of cover tree. All these three properties of cover tree must be satisfied when you're trying to build a cover tree. So now finally we are towards a slide that informs like what is the specialty of cover tree? Why is cover tree is the most efficient nearest neighbor searching problem? So what will happen is let's try to understand what is the problem with other nearest neighbor algorithms. So what will happen is the traditional methods like KD trees and ball trees partition space geometrically. So what will happen in this case, they perform well only in the low dimensional data, that is 2D data or 3D data, and they eventually decrease their efficiency when you're going towards the non-Euclidean spaces or we are going towards the high dimensional data. And then here comes the concept of cover tree. Now what will happen in cover tree is, in cover tree overcomes its limitations by using only pairwise distances, and it works in any dimension, not only three dimension. It works in any dimension. It provides high level of efficient answers and efficient time complexities. And then it also enables fast nearest neighbor search using only linear space, that is approximately log n time complexity for searching or for searching or for inserting for deleting. It will be taking only log n complexity, whereas other traditional methods would take computationally high complexity for higher dimensional data. So it will also, as we're trying to build the tree hierarchical, so pruning can also be easier as the distance between the child and parent is also less than 2 power I. So the pruning of data could be so easier in terms of searching a nearest neighbor, so that will be excluding all the other data and will be focusing all the required data. So here comes the time complex analysis of the power tree. So before directly diving to the time complex analysis, let's try to understand what is C here. As you can see here, in the worst case time complexities, we got a term called C. In this particular case, we called C as an expansion constant. It generally tells that represent how many by how the number of nearby points grows as the radius increase. For suppose we had a ball and then it has a radius r. What does expansion constant actually describe is by increasing the radius. For suppose you increase the radius from r to r, so to what level the data points will increase. For suppose before we have x data points, and then after increasing radius from r to 2r, what is the rate of increase of points from x to from another constant, like we'll take another y. So what is the ratio of increase between x and y by increasing radius? This is what expansion constant actually describes. So as you can see here, it means smaller q, it gives dense clustering and will get faster operations. As you can see here now, here comes the time complex analysis of cover tree. We'll start with a build tree. We need totally of n points. So building n points, and then in a tree would take generally for each point it will take in log n complexity to search or to insert. And then for n points we'll be needing n into n log n into log n. And then in the worst case scenario, we'll be requiring order of C power 6 into n log n. And to store all the n points, we need order of n space. And then it is same, as I mentioned before, it is same for nearest neighbor or insert or delete in the case of cover tree. All of them would be taking order of log n complexity in the average case. In the worst case scenario, cover tree would be taking to query the nearest neighbor, it will be taking order of C power 12 log n complexity. And then to insert and delete, moreover, they are almost same. They will be taking order of C power 6 into log n complexity. As you can see here, as you can observe here, the concepts of C power 6, C power 12, these expansion constant comes in picture only in the worst case scenario. Because in the worst case scenario, we'll have highly irregular and dense points. They were arranged in the coordinate plane, and then more nodes might be need to compare in this situation. So in this situation, we'll be getting a term expansion constant to understand this problem very easily. So we are finally towards the end of our presentation. So let's now try to understand how to build a cover tree using a problem. So here comes a data set. It consists of totally 7 points arranged from A to G. So what is our goal? We need to build three hierarchical levels so that we'll be building a cover tree. Now, what is the goal of our presentation? Goal of our problem? We need to build 3 points, three levels, namely C2, C1, and C0, where C1 is the pure purest, that is, it will have very less and very minimal view of data, and whereas C0 will have finest view of data. And then, as we have discussed before, what is the rule to satisfy this is we need to satisfy nesting property, covering property, and also separation property, which we have previously very well discussed. Now let's try to move to the solution of this problem. So let's try to understand. So totally we have three levels in our situation, and then each of them will have a scale of 2 power I, where level 1 will have a scale of 4, that is 2 squared, it is 4. Then what will happen is we had a scale of 4, right? We will be picking the data points that were greater than 4 units apart. So let's try to understand what are the data points. As you can see here, we can apply any distance formula. It may be Euclidean or Manhattan, anything. So as you can see here, there are data points A, then data point G, and then data point E. If you try to apply the formula, they would be greater than 4 units apart. So as we discussed before, now at level C we have totally 3 points. They are A and G and E. So this is our first set in the level 1. And then we'll move to level C2. Here the scale would be 2 power 1, that is 2. So we need to find the points that were greater than 2 units apart. And another property that we previously discussed regarding cover trees is it is nesting. What do you actually mean by nesting is all the points that were included in the higher level must be brought towards all the lower levels. So the same thing happened here. In the higher level, we have A, G, and E points. In lower level, we'll start with A, G, and E points. And then we'll try to check if every point in S is within less than 2 distance from some C1 center. If you apply the formulas, we'll come to know that points C and B are near G and A respectively, whereas points D and F are not within 2 of any current centers. So what will happen here is, as you can see here, since points C and B are within the radius of G and A, there is no problem. But points D and F are not within our scale, so we need to add them as new centers. So what will happen? Subsequently, we need to follow all other properties like separation and other property also. So the final set in the C1 would be like AGE would be continuing down, and then we'll be adding D, F, and B in this situation. And then we'll move to the next step, that is level 0. It is the final step where we'll have complete view of data. As you can see here, we have all the points in our data set, that is A, B, C, D, E, and F. Now let's try to understand visually what happened here. So as you can see here, C2 is a highest level where it contains A, G, and E with a scale 4. That is, the separation between any two points could be greater than 4. And then we'll move to the next level, that is C1. It is intermediate step with scale 2. What will happen is here, any step will have separation greater than 2 units, and then it has coverage of less than 2 from the centers. They are the A, G, and E. Here we'll include points A, B, D, E, F, and G. And then we'll include point B since it has coverage less than 2 from the centers, and we'll also include D and F as a new centers in this point. In this level, and then we'll move to the next level, that is level C0, where we'll include all the points. It is the finest level where we can see all the information about data, and here the coverage is 2 power 0 is equals to 1. That is, it should be less than 1 distance from all the centers. So this is about the course tree. Now what will happen is, after building this particular course tree, if you want to find a nearest neighbor, so we'll take a point, and that could be So, and then we'll follow hierarchical partitioning. We'll get only the values that are very nearer, and we'll remove the clusters that were far from our new query. So finally, we are towards the end of the presentation. Here comes the references. So I took the reference from the original query cover tree research work by all the authors. And then I also went through Wikipedia contributions about cover tree and made this presentation and a blog. So yeah, this is the end of our presentation. Thank you for listening. So towards the end of the presentation, I would like to thank everyone for listening all this time. And then I will also inform that I'll be adding the original paper of cover tree in the description of this video, and also I would be adding my particular blog that I have created. That blog that I have created, I mentioned all the points that we have discussed today regarding cover trees and also few new points. So I'll add the blog link also in the description. Please go through it. Thank you for listening all this time.